Continuing our discussion on the dynamic analysis of the slider crank, we now move forward to another topic in this analysis, that is determining the angular velocity and angular acceleration of the connecting rod. So questions are also asked from this category. That's why it's important to cover this topic as well. In the previous video, you saw the derivation for the acceleration and velocity and displacement of the piston. So now we will determine for the connecting rod. So angular velocity and angular acceleration of connecting rod means that you have to determine the rate of change of beta, the angle beta that you see here. So beta is the angle made by connecting rod with respect to the horizontal axis. Similar to theta, theta is the angle made by crank. So angular velocity of crank was d theta by dt. Omega was d theta by dt. So similarly, angular velocity of connecting rod will be d beta by dt. So we have the known parameters are L, R, theta and omega. So we have to find the expression for d beta by dt, that is the angular velocity of the connecting rod, in terms of these parameters. So first we have to find the relation between beta and theta, and then we can differentiate that expression with respect to theta to get the d beta by dt. So if you consider our figure, here you have two triangles PA B1 and OAP. So the common link between these two triangles is the link AP. So this is termed as y here. So y is equal to r sine theta, and y is also equal to L sine beta. So that is why y equal to r sine theta, that is also equal to L sine beta. So this will give us the relation between beta and theta. From this expression we will get sine beta is equal to sine theta multiplied by r by L. L by r was n that we determined earlier. So this becomes sine theta by n. Now when you want to find d beta by dt, you can take a partial derivative of beta with respect to theta and then multiply by partial derivative of theta with respect to time. So we are doing this because we know d theta by dt, this is the quantity omega, the angular velocity of crank. So we just need to determine d beta by d theta. So we will differentiate this expression to get d beta by d theta, differentiate both the sides. So d by d theta of this and d by d theta of this one. The differentiation of RHS gives us cos beta d theta, d beta by d theta, and the RHS gives 1 by n cos theta. So hence we find d beta by d theta is equal to cos theta by n cos beta. Now the angular velocity of the connecting rod we will term WC at present. This will come from here, is equal to d beta by d theta multiplied by omega. D theta by dt is nothing but omega. So angular velocity of connecting rod is omega cos theta by n cos beta. But here again we have the beta in the denominator. That is not a given quantity. Theta, omega and n are known, but beta is unknown. So we have to simplify the expression for cos beta. So cos beta we can write it as 1 minus sine square beta, that is from the identity cos square beta plus sine square beta is equal to 1. And sine square beta we can find from our earlier expression here. Sine beta is sine theta by n, sine theta by n. So you can substitute here. This will be equal to 1 minus sine square theta by n square. So sine, because sine beta is equal to sine theta by n by substituting this value. So we can substitute here and get the angular velocity of the connecting rod. Omega cos theta by n 1 minus n, you take n square in the numerator, do the summation, sine square theta, and will come outside also and then get cancelled out. So we get finally omega cos theta by n square minus sine square theta. So this is the final expression. So you need to memorize this formula for getting quick answer of an objective question, the angular velocity of the connecting rod. Now we are going to find the angular acceleration. For determining the angular acceleration, we have to differentiate the angular velocity with respect to time. So d omega c by dt, that we can do the partial differentiation and get d omega c by d theta multiplied by d theta by dt. D theta by dt is known as omega, the angular velocity of time. So we have to determine d omega c by d theta. So we'll get this quantity d by d theta and substitute the value omega cos theta divided by n square minus sine square theta. We will take this differentiation. This will be equal to, omega will come outside as a constant, d by d theta of cos theta n square minus sine square theta power half. So we are taking a simple multiplication of two functions. This function is power half minus half. We have to do term wise differentiation of first with respect taking the other constant, and then second taking the first constant. So this will come equal to omega. So we'll take the differentiation of this one first, taking cos theta constant, cos theta, differentiate this one differentiation will give you minus 1 by half this expression n square minus sine square theta to the power minus 3 by 2, because d by dx of x power n is n x as x minus 1. Then differentiation of this function inside. Differentiation of this function will give you minus 2 sine theta cos theta. Okay. Then we take the differentiation of the second term, treating the first term constant. So n square minus sine square theta power minus half will keep constant and take differentiation of cos theta, that is minus sine theta. So on rearranging and simplification of this thing, take n square minus sine square theta power 3 by 2 in the denominator, minus 3 by 2 outside, then inside you will get cos square theta plus cos theta and cos theta cos square theta. Sin theta also is common to both the expressions, so we will take sin theta outside, n square minus sin square theta. So this is a quantity, and here this will be in bracket. When you open the bracket, you will get cos square theta plus sin square theta, that will be equal to 1. So this will come out to be n square 1 minus n square. So d omega c by d theta will be equal to omega sin theta 1 minus n square divided by n square minus sin square theta whole to the power 3 by 2. Now the angular acceleration alpha is equal to d omega c by dt, that is this d omega c by d theta multiplied by omega. So multiply this expression by omega, and if following our standard convention, we will get minus omega square sine theta n square minus 1, because n is usually greater than 1. That's why we are taking n in this side and we are inverting it, multiplying by minus 1 and taking the minus 1 outside. So this quantity will become positive, and the absolute value you can get n square minus sine square theta will for 3 by 2. So the negative sign we have taken out to indicate that angular acceleration of connecting rod is such that it tends to reduce the angle beta. The behavior that the acceleration tends to reduce the angle beta is something similar to the simple harmonic motion of a pendulum, as you can recall. When the pendulum is in extreme position, the acceleration tends to bring the theta towards the equilibrium. So if the theta is towards this direction, towards left, the acceleration will tend to bring it towards equilibrium, that is towards the right. So acceleration always acts opposite to displacement. That is the characteristic of a simple harmonic motion. So the connecting rod is executing a motion something similar to the simple harmonic motion. So in the present picture, the beta was positive. So that's how the acceleration is in the clockwise direction. It is opposite to the angular displacement beta. So when beta is negative, then the acceleration will be bring it towards the equilibrium. So this is the equilibrium position of the connecting rod, which will come when you have the piston towards the inner dead center or the outer dead center. Now we will take some numerical problems for the topic of dynamic analysis of slider crank. So I'll take an example here. The question given is that the length of connecting rod, so the known parameter, that is length of connecting rod, length of crank, etc. L is given as 500 mm and the length of the crank is given as R is equal to 100 mm, and it is given that the crank is rotating at 400 rpm, 400 revolutions per minute. So when the crank position, when the crank has turned 30 degrees from IDC, inner dead center, then find. These are the questions. First, acceleration of piston. Second, velocity of piston. Third, angular velocity of the connecting rod. And fourth, angular acceleration of the connecting rod. So we will take on this example. We apply the derivation that we have learned just now for the slider crank. So R is given as 100 mm. We convert it to SI units, that is meter, so it will be 0.1 meter. L is 500 mm, that will be 0.5 meter. And speed of rotation, angular velocity, angular revolution per minute are 400 rpm. This we have to convert into omega, angular velocity. Because our derivations were done in terms of angular velocity of crank, we have to find omega, that is 2 pi n by 60. The number of revolution divided by 60, number of revolution per second multiplied by 2 pi is the angular velocity. So 2 pi into 400 by 60, this comes as 41.88 radians per second. And so R is known, L is known, omega is known, theta is given as 30 degrees. So we have all the 4 known parameters for the slider crank problem. The another derived parameter is N, that is length, ratio of length of connecting rod and crank, L by R, that is 0.5 by 0.1 is equal to 5 in this case. So we will just recall our formulas. For acceleration of piston, the formula was A is equal to R omega square cos theta plus cos 2 theta by n. So we are using the exact expression here. The simplified one was R omega square cos 2 theta by n gives the exact expression. We substitute the values here. R is 0.1, omega square 41.88 square, cos 30 degree plus cos 2 theta is cos 60 degree divided by n, that is 5. This we get 0.1 into 1753.93. You can use the calculator. 0.866 is cos 30 degree, cos 60 degree is half, that is 0.555. So if you do all the calculation, you get the value of 169.43 meter per second square. So you can get done like this. So that's why you have to remember the formulas, because you know the derivation, you know how to be solved, but for the examination purpose you need to remember the formula, then you can get the quick answer. Now the velocity of the piston, the second part. Velocity of piston was given by the formula, the exact expression R omega sine theta multiplied by sine plus sine 2 theta divided by 2 square root of n square minus sine square theta. So in this expression we will substitute our values. R is 0.1, omega is 41.88, sine 30 degree, theta is 30 degree, that is half, plus sine 2 theta, that is sine 60 degree, divided by 2 square root of n is 5 square minus sine square 30 degree. So if you do the calculation from a calculator, you will get a value of 2.458 meter per second. Now the third part of the problem, that is angular velocity of connecting rod. So this part will recall our equation for connecting rod omega. Omega C is omega cos theta divided by n square minus sine square theta. This is the equation we just derived some time back. So omega is known 41.88 multiplied by cos of 30 degree divided by n is 5 square minus sine square 30 degree. If you simplify, calculation will give you a value of 7.29 radian per second. So as you can see here, the angular velocity of connecting rod is quite less as compared to the angular velocity of the crank, which was 42.88 radian per second. Now coming to the fourth part, the angular acceleration of connecting rod. We recall the formula for angular acceleration of connecting rod. Alpha connecting rod was equal to minus omega square sine theta n square minus 1 n square minus sine square theta divided raised to the power of 3 by 2. We will substitute our values. Omega is 41.88 whole square, sine of 30 degree, n is 5 square minus 1. The denominator will get 5 square minus sine square 30 degree whole to the power 3 by 2. You get a value of minus 170.93 radian per second square. Now we take on another example from this analysis. So here again the parameters will keep it same for our simplicity. L is equal to 0.5, R is equal to 0.1, omega 41.88 radian per second, and theta is equal to 30 degree. Here the question asked is find the position of crank from the inner dead center, that is IDC, for zero acceleration of the piston. So here the question is asked in a tricky way. We have to find the position where zero acceleration occurs. So the first step in finding the solution is to find theta, or the position of the system, the angular position of the crank, for which the piston is having zero acceleration. We have to solve for this first. After getting that, from the theta we have to calculate the x, position of crank from IDC. So we know the expression for the x from our earlier derivation, but first we will go on finding the position of zero acceleration. So if you recall the expression for acceleration of the piston, it was r omega square cos theta plus cos 2 theta by n. So the acceleration is 0, so this thing will equate to 0. Then we will simplify what happens. So this thing 0 is equal to r omega square cos theta plus cos 2 theta by n. Now since r is not 0 and omega is also not 0, therefore this expression has to be 0, this whole expression. So we will equate and simplify. We get n, this will come here, n cos theta plus cos 2 theta is equal to 0. From this equation we have to solve for theta. So cos 2 theta, we use the identity is equal to 2 cos square theta minus 1, simple trigonometric identity, and cos theta here is equal to 0. We will get 2 cos square theta plus n cos theta minus 1 is equal to 0. So n is 5 here, so we will just replace it by 5 here. So 2 cos square theta plus 5 cos theta minus 1 equal to 0. This is a simple quadratic equation. The solution for quadratic equation is x. This is our x, our variable now, which you have to find in the quadratic equation. X square plus x minus constant. So the solution is, this is the term b. b is here 5. b square ax square plus bx. This is similar to, just write it here, ax square plus bx plus c is equal to 0. The quadratic equation. The solution for that is minus b, so minus 5 plus minus square root of b square minus 4ac. b square means 5 square minus 4 times a is 2 here, and c is 1 here, minus 1 here, minus 1 divided by 2a. a is 2 here, 22. So if we simplify this expression, we will get value minus 5 plus minus 5.744 divided by 4. Now here we get two solutions. One is minus 5 minus 5.77 and another one is minus 5 plus 5.74. So obviously the cos theta is less than 1 for all theta. So we'll discard one solution. Solutions possible are taking the positive value of 5.74, get 0.744 by 4, and the other solution is minus 10.744 by 4. So this is obviously greater than 1, so discard this thing, discard the solution, and we will keep only this solution. So from the calculation we got cos theta is equal to 0.744 by 4, that is equal to 0.186. So theta is equal to cos inverse of 0.186, which is equal to 79.28 degrees. So this is the angular position of the crank for zero acceleration. Now we have to find the equation for x, displacement from inner dead center, is x is equal to r 1 minus cos theta plus n minus square root of n square minus sin square theta. So this is the exact expression. If you want a quick answer, you can use the approximate also, r 1 minus cos theta. This is approximate. So we'll just substitute our values here. R we know is 0.1, 1 minus cos 79.28 degree plus n is 5 minus square of 5, that is 25, minus sin square 79.28. So you have to calculate this value. If you calculate, you will get an answer close to 0.082. So that is 82 mm. So at a position, angular position of crank theta is equal to 79.28, when x, the displacement of piston from inner dead center, is nearly 82 mm, the acceleration of piston becomes 0. So what it reminds us that the theta for zero acceleration is 79 and it is not 90 degrees. So in the case of the slider crank, the minimum acceleration occurs. This is IDC, one extreme position. This is ODC, another extreme position. It doesn't occur the midway between two, because for the midway, the angular position will be 90 degrees. So it doesn't occur at theta is equal to 90 degrees. Lead to zero acceleration. So our case is not a simple harmonic motion. It's something similar to simple harmonic motion, because in simple harmonic motion, if you remember the bob pendulum case, at the mean position, at the equilibrium position, the acceleration becomes 0. So this is not happening in this present case. At some angle other than 90 degrees, we are getting the zero acceleration. That is 79.28 for this case, and the angle, the value ratio of LNR basically depends on n.